I got more space questions, so feel free to raise your hand to answer. The first question is talking about the orbit of Mercury around the Sun, and then it described that the orbit duration is 88 days. This is the duration that Mercury takes to orbit around the Sun, and then the average radius of the orbit is uh, 58 million kilometers. So the average radius is around 58 million kilometers. Now they're asking you to calculate the average orbital speed of Mercury and give the unit that you're gonna be using. Okay, so who can help with this question? Million kilometers. Okay, let me just get to the chat 1 second. Tibian. Okay, let's go with Tibian. Okay, what is the formula you need to use?
Speed equals 2 pi r over time.
Speed equal to pi r over time. Okay. Now your time and r are given, right? So how can you substitute? Like, do you use the same units? You can use km and days, or you want to change the units?
Days to hours.
Okay, so this 58 million, how can you represent it using like a numerical representation, not just like millions like that? You can multiply by 10
To the power of 6.
and then divide by the days. So convert the days into hours. 24, right?
Yes.
Okay, what is your orbital speed for Mercury? And give it in kilometer per hour. So what is the unit? What do you guess for the answer?
173 times 10 to the power of 3.
Okay, okay, good. Everyone understand the answer, right? Now let's talk about comets, and the comets we said they orbit our sun in an elliptical orbit, so it looks something like this. And then the comet would be somewhere here. And then let's describe first, name the force that caused the comets and planets to orbit the sun. What is it? What do you guys think?
The gravitational attraction of the sun.
Yeah, the gravitational force, yes. The gravity, basically. Gravity. Or the G force. Yeah, and then add to the diagram opposite to show add a diagram opposite to show the orbit of a typical comet. I think that shows already the orbit, so this is the answer for okay. And then the speed of a comet changes during its orbit. On the orbit you have drawn, label with an X letter the position where the comet travels at the fastest speed. So where on this orbit, let's say it would have the highest orbit speed?
When it's closest to the sun, right?
Yeah, so probably maybe here. Let's compare distance. Maybe probably here would be the closest. Yeah. So roughly anywhere closest to the sun would be the highest velocity. So so probably if we say it has this orbit, oh, it's a give normal images. So let's say it has this kind of orbit. And then if we know that the sun is here, and then our comet is orbiting in this fashion, so probably it will be traveling at the highest velocity at this point here. So this is fastest, and then fastest, and then slowest here, slowest. Okay. Now explain why the comet travels fastest at point X.
Because when any object comes closer to the sun, the gravitational attraction or pull is stronger, so it starts to move faster.
So yes, the gravitational pull or the gravity pull, we can say that the pull is increasing, and then that would mean that the velocity would increase because the velocity is changing due to gravity. And then when it's moving away from the sun, then the gravity is reducing and it will slow down eventually. So another word that we had to talk about, probably conservation of energy. We have to talk about conservation. Oh yeah, conservation.
If we have to mention that point, how would we word it in a sentence?
Yeah, so you say the kinetic energy, which is the velocity basically. So the kinetic energy is changing due to, so we said that the mass of the comet doesn't change, so the velocity is changing, right? And
Yes.
then the change in kinetic energy has to be matched with a change in the gravitational energy or potential energy, gravitational energy or PE. So that energy has to match or balance whatever increase here. It has to be met with another increase in the gravity as well. So since velocity is increasing, we know that the gravitational pull is also increasing, yeah? And the vice versa happens when the gravitational pull is reducing, then the V is also reducing, the velocity is reducing.
Okay,
Yeah.
okay, I see.
So since you can say that Ke, the kinetic energy, the gain in kinetic energy and the gain in potential energy has to be conservative, which means if one increase, the other one has to increase. That's why if the velocity is increasing or the velocity is increasing, yeah, it's moving faster, then the gravitational pull has to be higher at that point here. What about, okay, speed of light is definitely related to space physics. Okay. So speed of light in vacuum is, we know it at 300,000 kilometers per second. Now the average time for a ray of light to travel to the moon and back is about 2.6 seconds. Show that the moon is about 400,000 kilometers from Earth. Okay, so if you don't, I think it's better to visualize first. Okay, first let's sketch. So let's call this Earth, and then the moon is here around Earth, moon, and then show that the moon distance is, okay, so this distance according to the description is 400,000, okay, kilometers. Now if we know that the speed of light is fixed at vacuum, is the speed is given as 300,000 kilometer per second, kilometer per second, and the time taken was 2.6 seconds, and that distance is basically describing two ways, so one trip to the moon and back, yeah. So this is length 1, L1, let's call it L1, and then to the other way it came back to L2, and both of them are equal to this value here, this one too, yeah. Now how can you prove this? Do you think you need to use the like speed equal distance over time? I think so, yeah.
Yes,
You
I
guys
agree.
agree? Okay, so if you say that L1 and L2 are equal, and then you can basically multiply 400,000 to be 800,000 total distance. So this is our D. Now the time taken is given as 2.6. So if we know that speed of light is fixed, when we do this mathematical calculation, our S should be equal to the same S that we know, which is this S. So what does that give you?
307,600 something.
307,000. Oh, 307,692.
92.
Okay. So does that make our answer close enough? I think it's close enough to 300,000. So that could be an error in the distance. So maybe the distance is not exactly 400,000 kilometer. Maybe it's an estimation. Actually, we can check. Distance from the moon. Okay. So it's not actually accurate. So maybe that's why the rounding up increased our total speed. Yeah. So this is an estimated distance, and then maybe the time also could be not so accurate. It's the average time. So average time maybe it's not so accurate too. Okay. Any questions on how to prove the speed of light and how to know if the distance is correct or not?
No, but I have a question about the first question that's not part of the space physics topic. This is the question B to that question. So are the topics interlinked? Like, is it from a different topic and then they linked it with space physics?
I think yeah that could I'm not sure if that can happen in your final like IGCS exam, but maybe if you are like in a school they can interrelate the topics to test your knowledge. I think in IGCSE there's usually one section that cover certain topics, so they don't really mix between space and let's say light reflection or refraction. I don't think they would test you like that. Yeah.
Okay.
Probably it would be more straightforward, yeah.
Okay.
Every chapter has a question on itself. And I think when we finish all the revision for different chapters, we can do like a full paper revision. So we see how the exam paper is structured, how they ask the different questions. Do they mix them in different sections or is it separated by topic, you know? So hopefully maybe next week we can start doing full past paper exams. Yeah. I think another approach to solve this question would be, let's say you now make the distance as the unknown, you don't know the distance, and you know the time taken is 2.6 seconds, and then you can use the speed to find the distance, yeah? So if you multiply 300,000 kilometer per second and 2.6, you should get the distance, and then your distance would be roughly around this number. So what is the distance if you multiply
780,000.
2 points? Okay, 780,000. Okay, and then divide that by 2 because we said it's 2 L's.
390,000.
Okay, so 390,000 is very close to 400,000. So that's another way to solve it too. Okay. Now, scientists measure the time for light to travel to the moon and back. They measure the time taken for the light to travel to the moon and back very accurately, but the time is different every day. Okay. The graph shows how these times change over the time period of 1 month. I think I'm missing one question. Okay. Where is the question? Actually, there's no question here. Maybe I bring that one to the page, so it could be that I missed one of the questions. The scientists also discovered that the average time for light to travel to the moon and back increases gradually every year. What further information did this give you about the orbit of the moon? Okay, so first of all, let's tackle this part first, even though there was no question. So, over the period of 1 month, the time changes for the distance or the light to travel from Earth to the moon. Yeah. So that could be because we have the Earth in the center. Oh, sorry. And then the moon is orbiting Earth. This is the moon. So the radius of the orbit, if it's changing, if it's not fixed, if it's approximated, then at some point, maybe it's not a perfect circle orbit, and I think it's elliptical anyway, so we cannot really assume it's perfectly circular orbit, and that means that the radius could be changing, yeah. So at some point, the radius can be lesser in value, and then that means that the time taken would be smaller, like this point here. Yeah. So that means at this point the moon is closer to the Earth, and then at that point 2.7 is at its furthest point from the Earth. So maybe 1 and 2. This is 1 and this is 2. Yeah, and it's a repeating pattern because the moon is orbiting every 27 to 28 days. So that's why you see this change over a period of almost 1 month. Yeah, cycle repeating. And then the scientists also discovered that the average time for light to travel to the moon and back increased gradually every year. That I'm not so sure. What further information does it give you about the orbit of the moon? That could be meaning that the moon itself is maybe moving away from the orbit, like the orbit radius is naturally expanding, but that I'm not so sure about because there's no information that I had in the lessons that we had that explain this. So we can search about it now.
Maybe it's linked to the theory of the universe expanding, so that
Yeah,
increases the distance away from the sun.
it could be, but I also read that the expansion is happening in the whole solar system, so it's not really limited to one object. So everything is expanding, and that means that the whole solar system is expanding. So imagine like you cannot say that your moon is getting far from you because also the earth is expanding in the universe as well, so it's supposed to be relatively the same rate, so there is no change of position, like they are still in the same range. And maybe we can read and confirm. I need to read and confirm, so let's maybe check. uh, why is the moon or maybe orbital period is increasing every year? I should have said every year. It says it's constant, which makes more sense, but I am not sure about this part. Further information. Okay, we need to research that on your own time. I think go read if there is a reason why the average time for light to travel to the moon has been increasing. So if the light is traveling more distance, that means that the moon is kind of moving away from the Earth. So is it related to the Big Bang Theory expansion of the universe, or is there any other reason? Yeah.
Okay.
So I would say, yeah, go do some reading on that. I will also do my own reading, and I'm not gonna give a definitive answer. Is it for expansion of the universe, or is there some other reason? Now, this is the same question. Okay. Another question is talking about planets and P, Q, R, and S orbiting a star. So they just gave a name for it, like a star, but not really sure which star. And then the first part is asking you what is the combination of planets and star is most likely to be, what is that combination of planets and star? What is it called? Anybody knows? So it's not a galaxy, right?
Is it the solar system?
Yeah, it's a solar system. Yeah, so it's a solar system. And then different solar systems will make a galaxy, right? And then many galaxies will make a universe, right? Something like that.
Yeah.
And then Milky Way is a galaxy as well. Now, planet Q has a moon. Planet Q is this planet. And then on the diagram, draw the orbit of this moon first. So basically, you can sketch it to be orbiting in this fashion like this. So then you can say this is the moon for planet Q. Now on the diagram, draw the orbit of a comet. So the comet's orbit is gonna be around the star, not the planets. And then it can be, as we said, an elliptical orbit. So maybe something like this. Yeah.
Yeah.
Can the comets and planet intersect in the same point? Like, can collide with each other? What do you think? From what you see here, we said that there is an orbit of different planets, and this is our sun. There was a comet here, and that comet is gonna do this orbit around the sun. So you see, it can actually collide with different planets, right?
Yeah.
If the timing where the orbit of the planet clashes with the orbit of the comet, then they can create a collision or like an accident where they collide. Yeah. Now let's see this part. So the planets nearer to the star takes less time to orbit the star. Suggest why.
Because planets that are closest to the sun are attracted by the gravitational pull, and this increases their kinetic energy, which increases their velocity. So
Yes,
their orbital time decreases.
correct. So you can say that they experience a higher gravitational pull, and also maybe they are closer, so their distance, the orbital distance, is lesser. Yeah. So if the orbital distance is less, that means that the time also the orbital duration can be less. Yeah. So less orbital distance and also less orbital duration, and
Yes.
that is due to the maybe high g-force. Okay. Now planet P makes one complete orbit during this time. During which time? Which time? So planet P makes one complete orbit during this time. Planet R makes more orbits than S. Planet R makes fewer orbits than Q. Planet S makes more orbits than planet P. Planet Q makes fewer orbits than planet P.
The answer is C. S makes more orbits
See.
than P because it's nearest to the sun.
Mm. So the other ones, planet R makes more orbit than S. Not really.
Yeah.
And then Q, it's between R and S. And then S and P. Okay, so C is the more realistic answer. Yeah.
Exactly.
Q and P. Or Q cannot orbit more than P. Okay. Now, as the planets orbit the star, the distance between the planets change. Okay. Planet P is 200 million kilometers from the star. Planet R is 50 million kilometers from the star. I'm gonna bring back the diagram. Sorry. Just give me a moment. Okay. Now, as planet P has 200 million and planet R, this is planet P, planet R is here. Calculate the maximum distance between planet P and planet R. So how to get that?
200 minus 50.
Mhm. Wait, this distance is the distance between the planets, right? From the star, sorry. So that is the
Okay.
distance from the star.
Yes.
200, 200 million, and then the other one is 50. Okay, the maximum distance between planet P and R. Okay, if you assume that the maximum distance between them is between the sun, sorry, or the star is 250, then once they subtract these two distances, then you get the distance between P and R. Yeah, I agree.
Yeah,
Yeah,
150 million.
yeah, assuming that this is the maximum distance. Yeah. Now calculate the minimum distance between planet P and R. Okay. Does it give you enough information? Okay, so
Yes, maybe because if R was in the other side, then it would be 250.
also, yeah, actually, then this one is not. This is not the maximum then.
Yes, this is not the maximum. This is the minimum.
Yeah, this is the minimum. So it's a good way to sketch it then. Yeah. If the center is here, this is our star. Yeah. And let's assume the longest distance would be when they are exactly like at the same point, but in a different opposite to each other. So R is this side, and then the P planet is here. The distance between P and the star is 200 million, and then this distance is 50, correct? So now it's 250.
Yes, and the minimum distance is 150.
Yeah, okay, makes sense now. 250, and then if the other case, we are talking about both of them being on the same side, yeah? Okay,
Yes.
so here it would be 200, and then around 50, we have the R. Yes, that makes sense. What about if the star is here, and then let's say we need to calculate like distance between R is here and then P is here. So that is the distance, right? Let's say it's exactly at 90 degrees. And you already know this is 200, this is 50.
Pythagoras theorem.
Yeah, would it be larger than 250? No. Is
No,
it?
it will not be.
No,
It will
less.
not be. Okay, so now I think any angle between 90 and like if we say it's here, it's definitely gonna be less. And then any angle that is on this side, it will not be larger than this, yeah, because this is a 180, yeah. Yeah, yeah, okay, very, very good.